Thank you for joining us and welcome to the Stantec Water webinar series. It is our pleasure to introduce Sandeep Sathymoorthy as our presenter today. He will discuss the evolving role of machine learning and artificial intelligence technologies in water management. I am Heather Dean, your hostess. During this meeting, you will be in listen-only mode. We invite you to submit questions at any time during the presentation. If you're joining via computer or your mobile device, you can do so by selecting the Q&A icon in the top panel of your screen. Your questions will be addressed following the presentation. And with that, Sandeep, I will pass it over to you to get us started.
Thank you, Heather. Really appreciate it. Thanks, everyone, for joining this webinar. Very much looking forward to sharing on machine learning applications in the water space. This is a very relevant topic and impactful to all of us who work in this area. Just a quick logistical note, if you don't mind, I'm going to turn my camera off just to have more space on the screen for the content. I will turn it back on during the Q&A. Before we dive into today's presentation, though, I did want to take a second just to draw your attention to the importance of checking our biases. We're all subject to unconscious biases as a result of our upbringing, the cultural norms that we're in, our education, experiences, and so on. Importantly, what we now know from the vast body of literature in this area is that some of these ingrained behaviors can indeed be amended or modified to affect positive change for ourselves and our peers and teams and so on. For those who have some interest in understanding their own biases, I think it's really valuable to do the implicit association test. The link is here on the slide itself. So with that, I'd like to move on with our presentation. What I'd like to do today is really weave three main themes together related to the role of machine learning in the water industry. What all the kerfuffle and excitement is about, and why many of us are looking at these technologies, AI and ML, as central to and essential to many future applications in the water space. Second, and importantly, I'd like to explore a little bit what the value proposition is for our industry. We're a highly regulated, public-facing industry with many layers, a complex ecosystem of technology delivery to end-use points. So I'd like to really explore where do these machine learning technologies fit into that system. And third, and I will say equally important to value, is understanding what water-specific challenges there are around application of these technologies. Many of us have already experienced, and I'm sure we will continue to. As we find solutions, we'll explore new ones. So I'd like to touch on that a little bit. So motivation, I think when I started to put this together, I was thinking about, okay, why is this an important topic, right? Why? Of course, I'm keen to share the information and the knowledge that we're all learning. I think in order to dispel, some of the myth and the magic that seems to envelope machine learning and AI applications, particularly in our industry, is what I've seen. There's too much being ascribed to and conveyed around what machine learning can solve, and often with black box-like magic pill approaches. This is absolutely not the case. Second, what I see and hear in the marketplace, whether at WEFTEC or other places and in broader conversations, is a lot of murkiness around what is being described as machine learning or AI. Everything from control algorithms to visualization, dashboards, etc., is all now being lumped and couched as ML or AI solutions. I think we may be confusing and confounding the language around what all this is, and introducing perhaps a little voodoo around, all this stuff is ML and AI, and let's, put it all in the same box. I don't think either of these aspects around, myth and magic and voodoo and too much value is healthy for a strong and sustainable position to introduce any new technology into our industry. We are very discerning and careful about the, but perhaps some would even say conservative as an industry in enabling technology adoption to happen. And it takes time. I think as a group, we all need to clearly understand what these new technologies are, the value they offer to reduce specifically risk and cost, and why these are potentially game-changing technologies. And I think once we can do this, then we can really take advantage of them. At the end of the day, I'll say that these technologies are all mathematics. It's certainly complex math, it's very elegant math, but it is math nonetheless. It's math that's a step change from what we've done for many years and applied in quite novel ways with computational power that we've not had access to in the past. So my overarching goal today is to focus on a small piece of this very large real estate, break the selected elements down into core components so we can understand where applicability and value lie. With the exception of one or two things, I'm really not going to be delving into the math itself, rather a focus on how we extract value from these technologies and build on our vast experience, many, many, many years using hydraulic models, biological process models, chemistry models, and so on. This is that next piece of the evolution. There are seven kind of broad areas of artificial intelligence. I'm only going to focus on one of these, machine learning, or ML. And for the remainder of the presentation, I will make every effort not to use the phrase AI. Rather, I'll keep using ML or machine learning. In particular, I'll focus on four broad categories of machine learning: supervised learning, unsupervised learning, reinforcement, and deep learning algorithms. The primary distinguishing factor and feature between these four model approaches and applications lies in how the maths model is calibrated or trained and validated or tested, and then what we can use them for, right? The vast array of, again, how we can extract value from them. So let's, for a moment, think about a thought experiment. What if we had this highly functional future prediction machine, a la Zorro or something along those lines, which can accurately predict when equipment will fail or when a particular type of load may come into a wastewater plant, or what the water demand might be in September of next year? We can recognize very quickly that having this future prediction machine has pretty significant implications, powerful implications for our ability to plan shutdowns, to plan maintenance, plan staffing needs over very long periods of time, and therefore now work with the teams that we have to optimize management of our assets. What machine learning technologies give us is the ability to dig into the information that we have, connect disparate dots of information, and I'll show some examples in a moment, from a wide range of sources, organize them, and then apply them to accomplish whatever goals are important for, excuse me, for the groups who are interested in it. Quite frankly, this is not something we were able to do with great efficacy in the past, because elucidating these embedded patterns and hidden connectivity between data, particularly data that are quite different and disparate from different sources, that is not a trivial thing to do. And this is something that machine learning gives us the power for. So if we map machine learning potential and applications in the water space and assess the types of things we can do to be sure, regardless of the subvertical. So we might be talking about water treatment plants, wastewater treatment facilities, pumping systems, big dams, whatever it is. At the end of the day, we have some assets. Again, whether these are reactors or filters or dams, these assets have some sensors and analyzers and monitors. In addition to this real-time data that we've now been collecting for many, many years. We also may have lab results or observations, photographs, things like that. So data that comes on the asset and from the asset through a variety of different sources. These data have some patterns embedded in them that one can learn and recognize and understand. And this pattern knowledge, of course, can be integrated with external data too, whether that's weather, whether that's the census or zoning information, etc., etc. We can then predict what's going to happen for some of these data sets. I want to know what my flow is going to do in the future based on the patterns that I've recognized from the past, as well as information on my new construction, in one neighborhood, for example. And we can inform a number of different stakeholders using this set of predictions and provide insight into the data itself. If we so choose, we can then do something more with this information. We can optimize the asset now using the predictions and using the data that we have to achieve specific performance objectives. Right. I can, for example, if I wanted to run a water treatment plant to achieve a target carbon footprint in December without compromising water quality, I can do that. This is a complicated set of pieces to put together in a jigsaw to achieve a particular objective. And again, emphasizing this is what the excitement about machine learning technology is all about. It's so well suited to do exactly this type of function. Once we have that optimized solution or approach, we can then control and manage each of our sub-assets or blowers or pumps, et cetera, within the asset itself. Right? So now I'm going to now go back to those four, so supervised, unsupervised, reinforcement, and deep learning, and step through them within the context of how they might apply in a system like this, for example. Excuse me. So let's start with supervised and unsupervised learning, right? These are, I'll say, conventional, now so-called conventional machine learning models. And this is what data scientists will call them. So in supervised learning models, the mathematical model that underlies a relationship between inputs and some outputs are learned through a training phase, right? And so again, just coming to the parlance of the machine learning and data science field, these input features, right, or, or predictors and the labeled outputs have some relationship between them, that it may be a one-to-one, it may be a many-to-one relationship. This can be learned by the model itself and built into a trained machine learning model. We can then use this trained model, take in new predictors about the future, and predict what the output will be. A really great example, and one that we've used for many years, is around regression modeling. So whenever we do a calibration curve, for example, for a DO probe or a or a turbidity meter, we are essentially running a supervised machine learning model. One important element or aspect of this supervised learning, of these supervised learning models, is that they are only of high value within the range that they've been calibrated to. So if we have a turb and I have calibrated this in the 1 to 10 NTU range, and let's say it's very accurate in measuring and predicting turbidity of samples in that range, uh, it is then not possible to use that exact same model and expect a high quality prediction if the water that I now have has an expected turbidity of 0.2 NTU, for example. So this is one of the limitations of supervised learning models. They're highly valuable. They're easy to calibrate and design. Pretty low bar for entry, if you will, but they're limited in application. In contrast, unsupervised learning models, in these models, the algorithm is built from data where the relationship between the inputs and the outputs is not mapped, and it may not even be clearly understood. And so these will be called unlabeled data, meaning that the outputs are not labeled to specific inputs. Rather, the machine learning model itself, through the training process, explores a set of rule structures and classifies them into groups which have similar characteristics or properties. You can then use that trained model, which has understood in the background without any coaching or training or supervision, hence unsupervised, from the human being. It can now recognize the connectivity between whatever it is that you're looking for. Admittedly, in the water space, we use this to some extent for dimension reduction. So principal components analysis is one example of that. However, it's not extensively used for a wide array of end-use applications. Rather, it's used a lot in the feature engineering to reduce the dimensionality of what happens next. So it's of high value, but in a sense, let's think of it as a back office functioner and player, right? I will give you one example where this could be used. If one is trying to replace some old equipment, let's say a pump that is no longer in production, and you want to replace it with a like pump, but you can't find that exact one. You can then look around in the marketplace and find the closest facsimile for your existing pump. And the machine learning model is very valuable to accomplish a task like this. So I want to move on now to reinforcement learning. And reinforcement learning is very interesting, and it uses a completely different approach from supervised or unsupervised learning. There's a fair bit here, so I'm just going to walk through this. In reinforcement learning, we actually call the machine learning algorithm an agent. So we anthropomorphize it a little bit, and this is the agent. The agent is acting in an environment. The environment may be, for example, an aeration basin with instruments and valves and controls and sensors, etc., etc. This is what's the environment, and what the agent does, the maths model, it's taking these observations in sensor data or temperature, etc., and it's classifying the collective of these observations into the state of the environment. Based on the state of the environment, the agent can then act a few different ways. Now, in addition to sensing the state, these observations are used to calculate a certain group of metrics, for example. If I take this aeration basin example, perhaps it's using the DO and the ammonia and airflows, etc., and the redox condition and so on to calculate a metric around what is the expected ammonia concentration in the effluent because of the current state of the system, right? Based on this, you provide the agent a reward, whether a good reward or a bad reward, so in quotes, a punishment, right? And the agent then modifies the behavior in accordance with the reward structure. Right? And after doing this numerous times, thousands, 10,000s, how many ever is needed, you do trials again and again where the agent does something, makes a new observation, calculates a new reward, and says, aha, I was rewarded. This is a good thing for me to be doing. So, now I can really understand what actions I need to take in order to be rewarded again and again. So this is a very novel way of learning, and in fact, it's how we learn as humans and other animals as well. The classic example, of course, is as a kid, if you just by chance you put your finger on the stovetop, it's hot. You take it back. That's your punishment. You won't do that again. Or the reward is that your hand is safe because it was just there for a few seconds. And it takes only one trial for us to learn not to do that. Reinforcement learning can have embedded inside it many different types of machine learning models. So you could run an unsupervised or supervised learning model as part of the actions, but it learns in using this particular mechanism. This is a very powerful way to learn. A lot of work has just begun in this area, and I think it will be a model and a technology that we have a lot of value for in years to come. I want to turn our attention now to deep learning models, and I'll focus on one type of deep learning model called a long short-term memory, or LSTM. This is one of my favorite models in this space. And all deep learning models use machine learning algorithms called neural networks, which are inspired by and really programmed to be close facsimiles of the human brains. And so each of these, excuse me, each of these has a layer of nodes, and each node is a mathematical function which are connected in a web-like fashion, right? That's how you can think about this. There's usually an input layer, what sensory inputs, what data are you taking in, multiple hidden layers, and an output layer of some sort, right? So the deep in deep learning really refers, it's a reference to that, the hidden layers and how many, how complex, et cetera, et cetera. And so I'll focus on one type, which is this LSTM model. And the reason is these LSTM models are really well suited for prediction of things which occur in the future based on some observations and measurements of the past and things that we are capable of measuring again in the future. So it's very good at handling sequential data and capturing both long-term patterns as well as short-term dependencies. So let's take a specific example. If I wanted to estimate the water consumption or demand in a particular neighborhood in a specific city next spring, so that one can plan water main maintenance, main feeder shutdowns, pumping infrastructure, management, staffing, CIP projects, et cetera, et cetera. This is high value because now I can be proactive about my planning. You could envision interrogating what was the consumption like over the past several years. So the output from the past or the thing that I'm interested in based on things like the flow, the demand the previous day or previous week. Maybe there were holidays, maybe it's the day of the week, maybe it's the evolution of the community. And you could explore the connectivity between these input of features and outputs. Now, some of those inputs may be measurable, others may be ingested from other sources, as we said earlier. And then with that understanding, we can train the model to predict what might happen in the future, and use some recent past data as our test case and assess how good it is. I think this model, the LSTM model, is going to have far-reaching implications for the water industry in years to come. And I think it's one that we all should start to really internalize and begin to understand and see where it fits in the zeitgeist of the water space. And one reason why I like it a lot is it learns in a very human-like way, if you will. And so I wanted to just dig into that very briefly. Um, when we input these predictors from the past, these measurables or otherwise observations or parameters, these features from the past, it goes into these memory boxes essentially. And the memory boxes are retaining some element of a long-term memory, so long-term patterns, as well as short-term things that happen. And based on the training data, deciding which of these and to what proportion they are important and relevant. Um, I will liken this for a moment to a personal example. If you ask me, what did you have for breakfast last Wednesday? I have no idea. I don't recall. But if you ask me what it felt like when my sons were born, I can tell you very vividly how that felt, even though it was so many years ago. And so I retain some things in my basal memory and others in my prefrontal cortex for a very short period of time. And I'm constantly shifting what things are there and what things reside in this long-term memory versus what I want to retain about the immediacy of the past. So if we think about a water use example, the LSTM model can integrate, long-term information related to patterns of water use, even non-stationary, meaning not the same over time, over long periods of time, and integrate relatively short spikes due to events. For example, maybe there was a sporting event that caused a little bit of a spike, and in the training model, while you're training this model, the model will then figure out, hey, based on the past, and this can be depending on how much of the past you want to retain, you can decide how much of that long-term memory is relevant and how much of the short-term um, dependencies I want to retain as well, and really fit and reduce errors between this prediction and some measured outputs from your validation or test set. I'd like to dig into some examples now and move on to the use cases and examples. And I want to stick with LSTM because, as I said, I think this has much relevance for us. So in our group, we've just begun working on what we're thinking of as an operator support bot. Imagine for a moment you have a bot, and an operator can ask something like, can I take train 2 offline for 2 months next summer to change diffusers and still meet permit? In this idealized world, the bot may return with an answer that says, yes, you can, but there's a 80% risk that you won't meet your ammonia permit or total nitrogen permit for 2 weeks. So maybe think about another time to implement diffuser replacement. So we started along this path and then realized, and of course, understanding this is a very complicated problem to solve. So we were taking it in pieces, and we had a little bit of success. In fact, we were able to predict ammonia concentrations from a plant to within 15%, several days out, but without really having a grounding in can we do this repeatedly again and again and again. So we started there, but worked backwards, peeling the layers off the problem and starting at the point of saying, okay, can we predict what is coming into a wastewater plant. So even though what I'm sharing here, and I'm going to talk about the specifics in a moment, is about a wastewater plant and prediction of influent flow, it has direct applicability because the conceptual idea and the math applied is exactly the same to water demand prediction, pumping demand prediction, equipment requirement prediction, systems or asset availability, et cetera, et cetera. It's got far-reaching implications once we can show that we can do this again and again. So in this work, our objective is to predict influent flow to a wastewater plant. And we've used about 5 use cases so far. We're expanding that, and these are all different sewer sheds. Admittedly, if you ask a seasoned operator, what is the flow going to be tomorrow? I think there's a better than 50% chance they'll give you a very good prediction because of their experience at the plant. So, it's not a very high value to have a bot to predict the wastewater flow tomorrow, but it's a good starter problem, because if we can solve this, we scaffold a lot of more complicated things from there. And if we can predict the flow over the course of a year, now that's impressive, and that's a pretty high value. And then we can scale that to not just time, but also prediction of performance of each unit operation in the system itself. So we started with these 5 or so utilities, very different sewer sheds, and built a model that consisted of an LSTM plus an artificial neural net, a feed-forward neural net to make the prediction. And our goal was, can we predict the flow 7 days ahead, right? For some long period of time. We picked a year, and how good are these predictions? And sort of linked with that, uh, how much data? We know that most machine learning models are data hungry. So how much data do we need to build this model? In addition to the LSTM neural net, so the machine learning approach, we also, in parallel, built an ARIMA model, which is autoregressive integrated moving average model, which is a statistical but not machine learning time series modeling technique that's been used for some time now. Also very powerful, and enables you to, really assess predictions of time series uh, data. So what we were able to compare a conventional statistical model with a newer machine learning model. Here are some results. So we're pretty happy with the results we have so far, and I want to summarize, sort of some of the things we've learned. So what I'm showing here on the left is the prediction in the orange line, and the data for one of the facilities, one of the 5 use cases we've begun with, which this one actually had a fair bit of variability in flow, so it was a good one to illustrate. The blue dots are the data themselves, and the orange line is the prediction. And these are predictions of 7-day look-ahead flows over a 1-year period, made on effectively day 0 on this plot. So here are some things we've learned. One, this will come as no surprise, having 1 year of data to predict 1 year of performance doesn't work all that well. And so this really reinforces this idea that this machine learning model, like other machine learning models, is very data hungry. Interestingly, though, we learned that having 3 years of reasonably high quality data is pretty much as good as having many more years of the data itself. So this was useful for us to recognize. And what this means is we don't have to, go to a utility and say, oh, I need 10 years worth of data to be able to predict flow into the future, right? And I think this holds value for all of us because, in many cases, you might have a flow meter change, you might have a something else, and as we'll get to in a moment on the data piece, good data are very hard to come by. The third thing we learned is that if you just want to look at a one-day look-ahead prediction, the ARIMA model is just as good. And as I said earlier, I suspect if you asked a seasoned operator, their model, their prediction would be just as good as a machine learning model. However, when we look at 7-day ahead, the machine learning model far outperforms the ARIMA model, particularly over long periods of time. And so drawing your attention to the plot on the left-hand side now, what we see is, from about day 120, let's say all the way out to the end, so I think it's about 339, right, is what this test set was. The model does pretty well at predicting what the flow should be with a great degree of accuracy. And you can see that here on the 1-1 plot on the right-hand side as well. But between day 60-ish and 120, where we had this big flow peak, the model didn't really do very well at predicting the absolute value of this flow. Interestingly, though, it does predict the shape reasonably well, up, down, up again, and back down. And that's what the model is doing, except it's hitting the wrong values. Nonetheless, being somewhat of an optimist, I think it's encouraging that the model is able to predict the shape. Now, the other thing that I would point out is these data, this orange line, is something that, if I look at the predictive power, was generated on day 0. So it's not that on day 60, we are saying there is going to be a peak and there's some degree of inaccuracy, more than some, maybe. And so the operator is really left with, well, this is not very good. Rather, we're saying at day 0, we're going to predict what's going to happen at day 90 with some degree of inaccuracy, right? So there is enough time to then, see, okay, this is directionally telling me what's going to happen. Yes, it may be wrong in the absolute value, but at least I know that this would be a bad time to do maintenance. Now, I will say very quickly, we're still optimizing this model to improve not just predictive power of these excursions and high flow events, but across the various sewer sheds that we're using as our test case. And our objective is to expand this to 10 different sewer sheds across North America, again, with very different characteristics, urban, peri-urban, and so on. Right. The next example that I'd like to highlight is some work from some years ago, and we're quite interested in the group I was in. We're quite interested in assessing the use of a novel bioelectrochemical sensor to monitor and predict the performance of anaerobic digesters. Really neat sensor. It's not a particular analyte or parameter. Rather, it's an aggregated sensor that's measuring the current status, health, etc. of biology. And so, this is a nice application to test. And as an add-on, we wanted to see, well, can we use this technology to predict what's going to happen? So this was a supervised learning model, one of the first ones I talked about earlier. And it's a multivariate regression model. In this case, it's a 3-parameter model with the following features. To predict the biogas production at this hour, for example, we used the previous hour biogas, measured biogas flow. We used something around the feeding characteristics of the digester itself, and we used a change in the signal, so a velocity, if you will, of the bioelectrochemical sensor itself. So I'm showing on the left the time course Orange, again, are the predictions. Blue circles are the data themselves. Really excellent prediction. Pretty easy. And again, I'll go back to this notion of, these models are easy to build. There are a variety of platforms in place that we can do it. We can even do this in Excel if we really wanted to, right? So easy to build. However, it's unclear to us that this model will be generalizable in that will it work in different systems, different mixing characteristics in the digester. So we expect that not only will the predictors be different, but perhaps the entire model structure would need to be different, which is one of the limitations of supervised learning models. It doesn't work so well outside of its own trained boundaries, right? I will say though that what we were really excited about, so we built this model and then were able to very quickly add on a heuristic essentially to retrain the model whenever the prediction got worse than a particular threshold. And so you can build in some intelligence into the supervised learning model, but it's still applicable to that particular system and will need to be reconsidered if you try and scale or cross-pollinate it elsewhere. So I'd like to look a little wide, through a little wider lens now, and just look at, some of the things that we could do with this. So I gave two examples, and I'll put them in the categories of flow and load prediction. Again, coming back to the four types that we talked about from here, from right to left, these are of increasing complexity, if you will. Flow and load prediction, you can use any and all or some combination of these models and learning techniques. Anomaly detection is another very important one that's been gaining a lot of ground in recent years, particularly anomaly detection of primary measurement data from sensors, one thing that I'll hit on here in a moment. Leak detection, using machine learning tools for design support and planning support, overall asset risk and asset health assessment, predictive maintenance, and looking a little further out, of course, everybody's very excited about twins. It takes all of these types of models to make the twin work and a whole lot more. Flood prediction is one that's emerging as an area of great success for these types of models. And I know of at least one startup that's working in the area of an operator coaching and training twin that allows you to do everything from scenario-based training to skills assessment and growth and so on. Specific use cases aside, and there are a lot, and one can populate this with a lot of different use cases and functions and value. What I really want you to see is we aren't at the stage where we have a whole bunch of established technologies and ML tools, right? Many of these are accelerating very rapidly. And so, it's important to recognize where we are in the evolution and maturity of this technology growth and development, right? One thing I will say is, if you try and map this to something like the Gartner hype cycle, which really has a model for adoption, it's likely that many of these technologies are currently in the so-called peak of inflated expectations, or some are coming out of it. I will say those on this side of accelerating, coming out of it and into the trough of disillusionment, because I think initially perhaps these were hyped up to do everything under the sun, and then this recognition that there are tremendous limitations around the maths, particularly, and I'm going to get to this in a moment, in our industry because of some inherent challenges. However, I will say that after a little bit of bumpiness, I'm certain, as are many others in our field who work in this area, we're going to build up the array of use case successes along the way and work our way to the so-called plateau of productivity here very soon. All of this to say, these attractions are coming to a screen near you, so be prepared. Right? So what does this mean? What does it mean? Be prepared to adopt these technologies. Well, I think it's worth thinking about that for a moment, but starting with this idea of what is the current state of how we manage our assets. Again, coming back to that, ingest data, predict, manage, control schema I showed you earlier. With our assets at the moment, we have online analyzers, we have controllable devices. We're very accustomed to using PLCs and SCADAs and such, right? But sampling, well, that's a lab function, and there's a manual connectivity between all the green groups. These are personnel groups. So how might machine learning play a role? Right? So I'll just give one view. There are many ways to slice this, but one view, and I've put this in two toolboxes. You can think of these as toolboxes which fit in or plug into some of our existing infrastructure. The first toolbox I'll highlight is around data management. We know data are noisy from many of our systems. We know they're, often not easy to parse. And so machine learning, again, supervised and unsupervised learning models, as well as deep learning models, can play a big role in pruning and parsing and cleaning up these data for us, uh, identifying anomalous data, filling the blanks, and then giving high quality primary measurements to do a variety of things with. The second, and this you can see in as a build up of the flow prediction example I shared a moment ago, where you can then take those data and through an analytics and process control toolkit, apply reinforcement learning, for example, and provide the operators actionable insights and recommendations to do something on the assets themselves. Similarly, you can provide those insights to the O&M, the M of the O&M team, and the lab team, perhaps something around that instrument is faulty, it looks faulty. I think it's time to do the following things. And all of this from a set of well curated data and good primary measurements. So what are some of the challenges around this? Well, to state the obvious, some are cybersecurity related challenges. This connectivity between on-prem devices or edge devices and cloud systems, well, this requires, careful thought in the cybersecurity. Not an area of my expertise, but we have lots of folks, across our community of practice who have lots of expertise in that. And then the other simple stuff, like, well, maybe not so simple. What if I lose power? What if I lose connectivity to the cloud and so on? So there are infrastructure related challenges for us. Also, not for nothing, but some of our equipment at water, wastewater plants and so on are quite dated. So you have interoperability and compatibility issues to deal with as well. The challenge that I want to highlight is around primary data quality. For many of the things we measure, so this is an ISC probe, for example. It's been in mixed liquor just a few weeks, and it has a lot of stuff on it. And I use that word very kindly. And as you can see, even with pretty decent maintenance and care of an ISC probe, the error compared to lab measurements can be quite high. I've drawn these lines around 15, plus minus 15%. 8% or so. So this really harkens to the old garbage in, garbage out. And for me, emphasizes while we are rapidly evolving all these tools and technologies around machine learning, our operators, our professionals are going to be central to utilizing these tools to maximize value, but also providing the right type of uh, expertise to ensure that these technologies perform what they are capable of doing. Things like instrument management, things like MEMS sensor replacement, just as an example. These are very operator and human relevant tasks and functions and aspects that we will have to make sure that we continue to do despite the prevalence of this novel, very exciting machine learning technology stack in our industry. So I think in the long run, we're going to be in a place where, perhaps in the future, the bot can run everything, this nebulous bot, but we will always need the humans to extract the highest value from the bot itself. Right? Really appreciate your time. I'm excited to take questions. I will turn my camera on and Heather, I will ask you to navigate the room for me, please.
Sounds great. So thank you, Sandeep, for sharing that excitement around the potential value of AI and
Pleasure.
machine learning technologies. We have a number of good questions here already. So I encourage you, our listeners, to keep those questions coming by typing those questions in the Q&A dropdown, which is located in the top panel of your screen. First question in today is, how do I choose the right ML model for my specific water problem?
Yeah. Um, I, I, I guess the simple answer is, talk to the professionals, but, hopefully I've given some framework or scaffold here. If it's a problem where you know what the mapping is between inputs and outputs, and it's a relatively confined space, if you will, supervised learning models are probably a really good place to start. They're easy to deploy, easy to calibrate and modify over time. If it's time series, LSTM or some other type of deep learning algorithm may prove very useful, particularly if there are very complex features that you're trying to understand the role of. There's some very good guidance, I'll say. Swan is putting some things out, but there's also on the IBM side, I think Tony will put some links in the chat. There's some really nice overviews of the model and model applicability. Also, speak to me, speak to lots of others in our field who are really thinking about this very question as well.
Thank you.
Thank you.
What are some common challenges in implementing AI and ML in water systems?
Yeah, I think I would say first and foremost, it really is the quality of primary data that we have. Many of our primary measurement systems are sat in environments that are hard and complicated. And I'll share a story of my own. Some years ago, I started working with a Silicon Valley company who has done a lot in the facial recognition space, and I was keen to collaborate with them and learn what they had. And so they brought a bunch of really good experts to solve a few things we were exploring. And after a few weeks of digging into the type of data, and it was just flow meter data, ammonia nitrate, pH, and DO from one aeration basin of 4. And they essentially said these data are lousy because they'd never seen so much noise, and this recognition that like our version of good data is plus minus maybe even 20%, and we've been pretty happy with that. And it's the spacing, the time spacing between them is quite long. And so this is, this is really something like the measurements we make with the sensors and monitors and analyzers. So all of that, let's call that primary data. It's inherently noisy. And this, I think, is one of our big challenges, and one that many of us are trying to really dig into to build this anomaly detection and quality detection functionality upstream of anything that we design on the machine learning control side. I think this is a big challenge. And then as we scale, I also think that the cybersecurity challenges will be something that we need to address, because these are public systems. The data need to be secure. We need to have surety of that. So really diving into what elements of this technology remains on premises versus in the cloud. I think there'll be some reshaping of that in the years to come. Sorry, I had a bit of a long-winded answer.
No, that's great. I know there's a lot of really fantastic questions
Yeah,
coming in. This one came in earlier. Have you incorporated the impact of weather conditions, so rainfall, temperature, etc., or dam release, if any, in influent flow prediction?
yes, great question. Yes, so our model, as it stands now, and as I said, we're still working on optimization. It does in fact include rain and some information on the date and the time and so on. And we found that those were sufficient to really get accurate predictions. The colleague I'm working with, she will correct me on this at some point, I'm sure, but I think we tried 5 or 6 different model structures and really gravitated to one trying to balance simplicity of data availability. Just as an example, if I just need to rely on precipitation measured past flow and the day of the week, these are easily obtained. But if I need to have more stuff, the data get more complex to obtain. But I also have potentially the value of more granularity and more and a better ability to decouple those long-term patterns with these short-term dependencies. So we're trying to find that balance at the moment. But yes, indeed, rainfall is included.
Thanks, Sandeep. I am being cognizant of the time, and we have so many questions coming in. We really want to stay on. So listeners, if you'd like to stay so we can answer a few more of these really interesting questions, please do so. Otherwise, we will send out some correspondence after. Just follow the chats for the remaining. Okay, so we have a two-part question.
Okay.
First part, can you provide some examples of ML application and leak detection? And 2, in the influent flow prediction examples, why do you think 3 years of data was enough? Having more did not improve the model accuracy.
I'll take the first one. So leak detection is one of those areas that's seen dramatic technology change just in the last few years. Sorry, Heather, you broke up. I didn't hear if the question was which technologies or what is the value. I just heard the leak detection part.
Leak detection. Sorry. The second part you're asking?
No, the first part. Just the audio broke up for the moment.
The first part was, can you provide some examples of ML application in leak detection?
Yes. So even at the household level, right here in California, there's a small startup in San Luis Obispo that has a device that you can basically strap onto your pipe downstream of the meter, and it is keeping track of your use and times when it detects anomalous water flow and says, hey, there's something wrong here. I apologize, I've forgotten the name of the startup, but I will get it and we'll send it out in the correspondence. There's also a technology, a company called Wint, They also have a really neat device. So these are point of use or home scale that I think has seen this rapid growth just in a short time. And there are also technologies being used at the system scale. In fact, some of these companies play in both spaces and have an adjunct meter effectively, or a way to measure whether that's acoustic or otherwise, what's going on with the system to intuit whether there are leaks or not. And really, so-called non-revenue water is a very big space of growth and application for machine learning models in the water space. And the second question was, sorry, Heather.
No problem. In influent flow prediction examples, why do you think the 3 years of data was enough and having more did not improve the model accuracy?
We think this is really an inherent function of the LSTM, meaning it has the maths has because of the sigmoidal function and the hyperbolic tangent function embedded in each of those memory boxes, it's learned enough about the long-term dependencies that it doesn't need more information to reinforce them. The caveat, of course, is perhaps this is a function of the particular time scale that we were looking at. So one of the things we're doing some experiments around now is if I move my test period later or earlier, am I getting the same high quality result? And the preliminary results we have back is yes, we are, suggesting again that this LSTM mathematics is robust enough that it needs just some insight into longer term patterns with these shorter term spikes and so on, and that's sufficient. You don't need to keep reinforcing the same things again and again and again.
Noted. All right, I'm going to ask just one more because they keep coming in, which is so fantastic.
Yes, this is wonderful. Please reach out after, folks, if you want to. I'm happy to talk about this.
Yeah, so I'll just ask one more. How do you train an anomaly detection model?
You provided data, so you provided unlabeled data, and you can train it a few different ways. So one, you can say, look, let me take a specific example. If I have a turbidity meter and I know the range of operation of the analyzer itself, of the meter itself, I can use that to qualify everything within these bounds should be pretty good. And this is my expectation of performance. That's one approach. And then I can say anything outside of this expectation is certainly non-performant. And so go and, map the spaces that are good and bad, and everything in that bad zone is anomalous. You need to then turn some knobs in there to make sure that you're getting the right percentage of good versus anomalous data. The other approach is you can actually feed all this in with other parameters, perhaps. So in the turbidity example, if you can also get the millivolts from the device, and you can get a status on the capacitor, on all these things, which now you can through things like heartbeat and so on, and feed that into your model, it will recognize the patterns between them and say, this appears to be the organization of information. And then you can say, well, when I saw this particular observation, it should have been X, but it's actually Y. So I'm going to call this anomalous. I'm going to call this anomalous. And once you've identified it, now the machine can go and prune the data to give you that organizational structure and what causes it, because you don't know what caused it, but it will find the connectivity between them. Just as an aside, there are also mathematical approaches you can use, including things like Haftinger's bounds and so on to understand the pattern of what's happening and expectation, and you use that. And then yeah, there are other very elegant mathematical approaches too.
Amazing. Oh my gosh. So the questions keep coming in. We are going to respond to those questions here shortly.
Okay.
We do
Yes.
have everybody's names, so you will have a response to that. We are going to wrap it up today. So thank you, Sandeep, and thank you all for your participation. If you have any other questions for Sandeep, his contact info is located in the chat. You'll receive an email shortly with your participation certificate. We will also be posting this presentation on stantec.com if you'd like to listen again or share with a colleague. Check out the link in the Q&A panel where you can find previous presentations from Stantec's 2024 Water Webinar Series. And finally, we have some exciting news to tell you that we are busy building next year's webinar calendar. We'll be posting our first couple of events in December, and we look forward to you joining us again in the new year. And with that, happy holidays from Stantec.
Happy holidays all. Be safe.